So good morning. I think it's going to be a lot of topics for you today, like switching between computation and study of correlations. So I will have 3 sessions, as you have seen during the school. So first, I should tell you a little bit about like the 3 topics I'm going to present and how they kind of come together during the lab. So then you will have a better mind map of what's going to happen and when. And then I'll tell you a bit more about like what we are exactly going to study this morning. So the 3 topics. The first one is device independence. The second one is the use of SDPs, and in particular sum of square proofs. And the third topic is going to be representation theory. Maybe just before we start the whole thing, I will kind of check the temperature of the room by asking you if you had prior exposure to a few topics. The thing is that I will do 3 sessions. They will be mostly whiteboard talks. I will maybe do a few demonstrations during the session on the computer if time permits, but most of the computing stuff will happen in the lab, where you will have like guided exercises. So a few questions. Who has been exposed to convex optimization, things like linear programming, semi-definite programming? If I say linear programming, who knows about what is a linear program? So that's very good that I know this information. It's maybe like 5 people in the room. That means that during the next session, I will take more time to explain the definitions and not, like go full speed on the topics. My second question is like the topic of representation theory. I can address this topic 2 ways. I can either give an introduction to the mathematical theory, or I can, if everybody knows about already the definitions, then I can move to applications. I much prefer, if you haven't been exposed, that I do kind of an introduction, because the software that I'm going to present, you can play with it and you can learn about the theory much faster than if you just use a textbook and pen and paper. Who knows about who has like a course in abstract algebra, like groups, monoids, okay? Who has used like group and representation in physics? Okay? Just a small question. What's the background of people here? Like, who comes from a computer science background? Okay, who comes from like more like a math background? And a physics background? Okay. So I think I will switch gears for this third session, and we'll do more like an introduction to representation theory. Of course, I'll tell you how it applies to the rest. But that's very good, because whatever you do afterwards, even if it's totally unrelated to quantum information, representation theory is something quite universal. So by having this, you will gain a few hours in your learning. So we have 3 pieces. They are very different. I want to tell you, like the first one, I'm going to tell you about how we can study physical system just by observing the information that they give us, with making like very little assumption of what's going inside the system. So it's a very new viewpoint in physics. Normally, physics is all about building models, making a lot of assumptions, and it's like the story of somebody asked a question about a cow, and the guy said, "Oh, assume a spherical cow." Physics is all about like making crude model and then being amazed that they actually work in practice, and then they match experiments so well. Device independence is a different viewpoint. It's like, what can we tell about the system if we just have access to the information that system gives us, like by doing measurements? But we are never going to assume exactly how these measurements work or what's going inside the devices. So this is why it's called device independent. Like we don't assume anything about what's going inside the box. STPs, or sum of square, they are a computational technique. Because what's going to happen is that I will give you a few examples there, but if you want to do research in the topic, some people don't use a computer at all, but they start to be in a small minority. So a lot of us do numerics to explore the field, but the problem is that you will run into computation problem very soon. All the examples during the lecture, they will be pen and paper, but if you want to do actual research, most of the time you need to use a computer. SDPs, they are a class of optimization problems. Optimization, it's a theory that has been developed when people started to planify the economy, like either in the States or in the Soviet Union. I have a factory, I want to maximize the production, given that I have these many machines, these many employees, and employees can't work more than 8 hours a day and so on. So you put a series of constraints and you want to maximize some objective, and you want to see what can you solve efficiently. And SDPs, they are a class of optimization problems with a certain structure that can be solved very efficiently on a computer. So this session is going to be about how do we solve polynomial optimization problems, find the maximum of a polynomial. But actually, it's a problem that is very difficult to solve on a computer. So we will see a few methods to approximate the solution. So this will be all about like how to maximize polynomials. Again, even if you don't go do quantum information later, this is going to be very useful. But of course, it applies to quantum information because a lot of things we work with can be seen as polynomial, but because it's quantum, things don't commute. So it's polynomial in non-commuting variables. Then what you realize that when you want to solve quantum information problems, you still run into limits for computation. So that's often the problem of like what we do when we speak about device-independent algorithm theory problems. We run into walls. But sometimes we can just manage to solve a few toy problems, publish a paper, and the people and when of course we advertise the paper, a general technique to solve blah, but actually it's a general technique only to solve the toy problem, because anything beyond you will need like a cluster to run it. So representation theory is all about using symmetries in those problems to gain at least a few steps more of computational power. I wanted to put these two topics because I recently released software that can address them. I don't think many people in the community use them already. So by exploring them, using them, you have chance to find things that people haven't found before. So this kind of like when I go to a school, like I'm asking myself, what can I give to people that if they brought somebody else, then would not have been there. So that's kind of my stuff. But what I will talk about like this morning, device-independent quantum information. It's a topic I work on, but it's like most of the techniques I will show, like half of the techniques I will show have been developed by colleagues, and it's something that's right now taking off. It's going to be a new viewpoint, and it's also very simple to start working on it. So that's really cool that I can come to this school, present things that will be quite easy. But then, if you want to explore around, there are a lot of low-hanging fruits to pick. So if you want to do a bit of research, it's probably way easier to start there than other subfields of quantum information where you have to read like 10 years of literature before starting. So that's a bit like for the schedule that we are going to have. Now I will say a few words about like device independence and the motivations. So the idea is that we will assume that physical system as just like boxes. So you get something in your lab, and on that box you can do measurements, and you will get outcomes. So like the simplest thing you can think of is that you will get like a bit of information out of your system. So then often we write letters for system A, B, C, and then I will write with lowercase like the result of the measurements. Okay. If you have just one system, it's not going to, you can't draw much conclusion, but we'll see later how it works. And a key point is that we will build models, causal models. They correspond roughly to explanation of what's going on. And then when we have some data and we have different explanation for that data, like model 1, model 2, and 3, the thing is we will never be able to say that this is the correct model, because it's not something that science can say that this is the truth. What we can say is that this data is not compatible with this model and maybe not compatible with this model. So what remains, or like one possible explanation is this one. So we will be able to say on that class of model, the only thing that fits the data is this explanation. So one big question that we will have is that we will take some data and we will build two kinds of model. The first type of model will be model that come from classical physics and model that come from quantum physics. Physics models. And our goal is to find situation where, based on the data, you can say, what I have is not classical. Of course, it doesn't prove that the world works according to quantum theory. Maybe there is a theory that will come after that. But what we can say is that often people don't like quantum theory because there are like weird aspects in it. And they want to go back to a model where information will be classical and things behave in a similar way. We'll see later what this means. By using those device independent methods, what we can say is that you will never be able to recover a world view that you like. So you have to deal with the weirdness of quantum physics, even if you go to a new theory that would maybe explain the world better. I should say a few words about Bell. So the story goes like this. People build the quantum theory first half of the 20th century, and there are a few aspects that a lot of physicists did not like. For example, this idea of entanglement, that if you have two particles that are separated by a certain distance, then you can't describe the two systems independently. You have to keep a joint description of them, basically entanglements. So there were a lot of discussion, like, will there be a theory after that that will resolve those problems and come back to a description where when systems are isolated, then you can basically describe them independently and it doesn't matter for your description. What Bell showed in 1964, and the idea is to do a simple experiment where you have two boxes. And the thing is, you have here and here, and you have a system that's shared between the two labs. So that would be here the first lab, and here the second lab. And what you do, you receive a physical system, and you're going to do a measurement on the system. But as an observer, you will choose between different measurements. So the X is going to be the choice of a measurement setting. A is going to be the outcome of these measurements. And you realize that I put some arrows. It means that the measurement that I do here depends on the physical system that I receive from some source that's shared between the two labs, and the choice of the setting that me as an observer am doing. So here I will get some data out of that, which is the outcome A and the choice of measurement X. And then there will be my colleague in a different lab, and this colleague will get measurement outcome B, and he will have chosen a measurement setting Y. This measurement will be done on a system. And the kind of physics that people wanted to keep and preserve is physics where you have, when this physical system was created, there is some information in it, and then now that information is shared between the two labs. But it's classical information, like it's a description that I could put on a computer using a series of bits, or something I could write down in a piece of paper, because I would know everything about the system over there. And then what happens in both labs is just information processing when I do the measurements. This idea that information propagates and the processing happens only with the information that I have right now, right here, it's called the principle of locality. This is a principle that dates back to Newton. When Newton discovered the theory of gravitation, people were already puzzled, like, how does the moon know the Earth is over there and how it should move? And people thought that, there should be like information carriers between Earth and moon that would kind of tell the moon where the Earth is. So this theory here would preserve this principle of locality. The only processing that happens there is with information that's shared actually between the two labs, because this information was created when the system that's shared between two labs is produced. To make this a little bit less abstract, experiment that can be realized in this way would be, for example, here you have a laser, here you have a crystal that would create two photons out of one photon that comes out of the laser. Then you send that photon to the two labs and you do measurements And this choice of setting would be what polarization do you measure your photon in, and the outcome of the measurement would be which polarization it is, for example, horizontal or vertical. And then at the end, you collect some data, P, A, B, X, Y, distribution of probabilities, and then you check, is this compatible with this model or not? Don't worry if you don't get everything that's on this picture. It's basically what we will explore all morning. And what Bell showed in 1964 is that there is an experiment you can do if you replace this by a source of quantum systems, and it will not be compatible with this explanation. Doesn't mean that quantum physics is correct, but it means that a view of the world where all the processing of information happens locally and I can know everything about the system, it's a viewpoint you have to abandon. I will erase this. This was just kind of an idea what this fits. Maybe just before erasing, what's interesting over there is that you think of everything as processing of information, but you make absolutely no assumption that the things in your lab are photons or that the measurement will be done in this specific way. You just look at information you get out. I will erase that. So that's basically what we have that happened in the quantum world. Let me say a little bit about what happens in the study of causality. Because those diagrams with like arrows and variables, they come also from statistics and the study of causal relation between things. And one, like it's the example you see everywhere. As a relation between cancer and smoking. So people said, okay, maybe if you smoke, then the model is going to be maybe you have a higher chance of developing cancer. But people said maybe, you know, I observe these two variables, smoking and cancer, like am I smoking? Am I getting the cancer, let's say at age 70? But maybe actually my explanation is the reverse. I have cancer, then actually I really want to smoke because I feel very anxious. So how are we going to describe those things? So here we would just have two variables. It's basically true or false, am I smoking or not? Did I develop cancer at 70 or not? So the variable S is going to be 0, 1, and the variable C is going to be 0, 1. And how do I do my observation? Basically what I'm going to do is to look at some subset of the human population and check what's the value of C and what's the value of S. I'm going to look at person 1, person 2, and so on, and I will get a series of samples. Then I can count how many of S and C did I get. And based on that, I will estimate some joint probability of S and C. It's going to be the number of events for each of those values divided by the total number of samples that I have. And then I can do, so now this is the information I get, and I can check whether the data that I get is compatible, let's say, with model 1 here or model 2. You will see that for that particular example, we run into a problem. Because there is something that will kill us is that we don't have enough structure here to say anything. So the thing is, I will need some different colors, and this is all black. If I don't have colors, then I'll switch my way. But there were some. Oh. Okay, let's check what we get. Well, it's like very fine, but it's okay, or blue. So for that model here, the distribution, they should satisfy that I have a probability of S, like no arrows coming to S. So everything I have to know about that system is basically what's the probability of being 0 or 1. I can't know possibly anything more. That system received an arrow from S. So the thing that I'm going to look at is what this box is kind of processing information that comes from S to give an output. So I need to look at the probability of a particular C given S. And then for that model, the joint probability can be described by just multiplying things together. You will see very soon why this model is not very interesting, but it's a good example to explain the notation. So here, C has no parents in the graph, no arrows pointing to C. So all there is to know about C is P of C, but no S. I need to write, because there is an arrow pointing to it, P of S given C. And then the distribution P of SC is basically P of C, P of S given C. But now the trick is that we have bias rule. So bias rule, what it tells us is that P of AB, okay, now I see why I should not use this color. Plus it doesn't erase well, so this goes on holidays, and we will start. So whatever distribution of AB I have, I can use bias rule and just say that this is PA times P B given A. And this doesn't assume any causal relation. This will always hold. So what it means that whatever observation I make here, I can use bias rules to move the PSC into this form or this form. So what we just prove is that these two models are completely equivalent. So actually, if the only data I have is that do people smoke, do people get cancer, and I have the joint distribution, I can't distinguish between the two. I need to have more, maybe add intermediate observation, like do people have a lot of tar in the lungs, like last week I was at a conference. People show that if you can have this additional variable in the middle, under a very mild assumption, you can actually conclude things. But here with just two variables, we can't say anything. I will show you two additional models, actually one where we can say something and one just to prepare what's coming next. I will just erase that. But maybe before I move to the next two models, I just want to make an observation. Here, it's not exactly an equality that when I observe a series of samples and I estimate a probability distribution by just doing this, what I get is not the probability distribution of the real thing. What I get is the estimated frequencies. Small question, who had a course in statistics? I did not as an undergrad, so I should not speak about statistics because my knowledge is really low. But who got like a class in statistics? Okay. It doesn't matter much because everything that we will talk about this morning is idealized systems. So what I will assume always, it's kind of, we can observe a population of like infinitely many people, take infinitely many samples, so that this becomes exact. So usually in quantum information, it works this way. People will first work on idealized systems, and then when they find something really nice, like a nice idea for an experiment, then they will bring in statisticians that will make the test robust. But usually we will not deal with the problem of having like finite samples and having statistical noise. So I'm going to remove this. Two additional models that we can use. Model 3 would be there is maybe something in the DNA that we don't know what it is, that will cause people to actually like smoking a lot and will increase their risk of getting cancer. Again, in this model, I could, because I have a variable there, I could actually put the value of S and C here. And this is as general as this model or this model, so I'm not able to distinguish any of these three. But this is something that will come later, that my distribution of P and C is basically some thing about the DNA. And now S will depend on this variable D. And C will depend on this variable D as well. That's also a totally valid causal model that I can build. Later on, we will see things where we will have like major differences, but right now it's just like warming up. And there is a fourth model. If I just put S and C like that, here what I know is that P of SC, because there are no arrows, those variables are totally independent. And now this is something that will have a difference because, for example, I have no way, because I have no link between those variables, to always correlate them. So for example, the distribution where I have PSC00 equal PSC11 equal 1/2, like half the time they all say 0, half the time I always have 1. This is incompatible with that model. Any idea how to test something like that? So if I give you a PSC, how would you test that condition? Any idea? I can show you one, but I don't know. Actually, I haven't thought of like what's the simplest way of doing that. So you have a distribution of SC, and you want to check if it factorizes into two independent variables like this. Yeah. Yeah.
Well, you need access to the two marginals.
Okay.
Then if you took a product, you might end up with a joint.
Okay.
That's the reason test.
Yeah. Yes. So what I would do is to compute this PS of S. So now this is something where I only observe S. But let's say I only have access to PSC. What I do is that now I'm not observing C anymore. So I'm summing over C. I'll do the same with PC. Now I sum over S. And then I check whether my PSC is equal to now, like I put this here and I put this there. S of S, PC of C. So this is a test I can do quite easily. Just a question. Here what I have written is the marginal distribution of the joint distribution PSC. Who has seen already that? Who is familiar with that kind of taking the marginal of distributions? Just raise your hands. Okay. The problem is that I'm working with this all the time, so I assume it's easy. What I want you to do, like normally I can read on people's faces, but so if I see that, I will ask you like to confirm that it's okay. I don't want you to be lost. Like the goal of these lectures is not to tell you about like the new exciting shiny thing that is at the top edge of research. It's to provide you a ramp so that you can start reading papers. So I'm not worried if I can't show you the latest exciting stuff, but if I can work with you like on notation and things like that, and add this staircase to the publication, my job is done. So yeah. Let me check where I was. Good. And what's the timing? So we started, yeah. Okay, excellent. I want to say that thing about what's in this viewpoint of like building those models, what's going to be the difference between quantum information and classical information. So the idea is this. Classical and quantum. Classical, so I'm going to take this example, like, but instead of having DNA and smoking and cancer, just take them as like abstract things now. Yeah.
So you define all these models under the heading of causality.
Yes.
So all of these are like, if they're all equivalent, then there's a cause producing the effect, or not related to causality.
So the idea is this: we build all possible models for particular experiments, and then so checking whose are equivalent is really good, because then I know I don't need to test all of them, just one of them. And if I show that it's compatible, then I don't need to check all the others. Okay, here for model 1, 2, 3, we prove two things. We prove that model 1, 2, 3 are equivalent, which is one thing. But in that example, there is something that is not nice to study. For the study is that all these models, they can reproduce everything you see. So it means that whatever experiment I do, this is always a possible explanation. But what I said later is that if you do this particular observation that these variables, they always take the same value, the only thing you can say in that situation is that this model can't work, where you have no link between the variables. Of course, yet maybe you don't see the point of that example, because being able to tell in an experiment, okay, smoking and cancer are unrelated, to everything that we observe that there is a link. So we have to say that, like, the only thing we can say in that situation is that there is a link between those two variables. We are not able to say more. Later on, I will show models that are more interesting in the sense that with two variables, there is not much you can do, but with three variables, it becomes interesting, and actually, we can't solve the problem completely. So you see, we go from something that's very trivial to something that's actually incredibly easy to state and incredibly difficult to solve in a matter of like a lecture, which is pretty fun. And so here, all the arrows I put, would be like, there is some information on your body, like let's say this DNA would be a bit that's 0 or 1, and that will have an influence on things that happen later. And that would be classical information. So what I will do, you realize I put like over like DNA, I put a circle, because I said something we can't observe. Let's say it's maybe too big to handle. So we will put those variables as something that exists, but something we don't observe. The only thing that we are going to make hypothesis about is that what are the links between those hidden variables that we can't observe and the things we observe. And by the way, we are going to treat quantum states the same way. We are going to assume that we can't observe a quantum state, or that we can make measurement of it, but we can never say everything there is to be said about it. We can just observe the effects of the measurement that we do on the system. So classical, there is something interesting, that if you have a piece of classical information, you can make copies. And then you can do whatever processing on that. But like the value that you receive here, lambda1, and the value that you receive there, you can make perfect copies. This is how we can transmit information across the world, that you receive a classical signal, an email or whatever, it's a series of bits, and maybe the signal was quite weak, but you can always use an amplifier to make a lot of copies, send them through the optical fiber, or the wire, or across the waves, and you can retransmit that information. You can even do like error correction and so on to be sure that you transmit the thing. With quantum system, that's not the case. You can't make a copy that would be perfect and send them to systems. This is called the no cloning theorem. Okay, what I said this morning is that I will not do quantum. It's all about like classification of classical systems. But if you were to study quantum systems with the same tools, you can't do these kind of things like take one system and broadcast it to a number of devices. And this is what we are going to use in the remainder of the lecture to characterize exactly what is classical, what classical system can do. And as I said at the beginning, our hope is to find an experiment where those classical models can't reproduce the observation, but it's compatible with, we know because we build it, it has a quantum model. And then we can demonstrate the power of quantum physics, which is always something that people strive for. Like, find a minimal example, the minimal experiment you need to do to show that the world is not classical, but that could be described by quantum physics. So that was no cloning. This is how it will go. Checking the time. Then I'll make a small break here, asking if there are like remaining questions about this, and I will move to like the next topics if not. Okay. What can I erase? I will erase this. I will erase that as well, and I'll keep just this for the sake of it. one. And actually, the scenario that I'd love to talk to you about, we call that the triangle network. And it's a scenario where you observe only 3 variables. I think some of you have been exposed to the Bell theorem, like the PAB given xy. That's already 4 variables. The triangle is simpler in a sense. And the big question that we had was that, can you demonstrate the power of quantum physics only observing 3 subsystems, like three variables? And the answer is actually yes. But we don't know what these variables should be to still demonstrate an advantage. What I'm going to speak about today is when those 3 variables only are bits. So it's like you have 3 systems, you always do the same measurement on them, and each measurement has only 2 outcomes, like let's say 0, 1, or polarization with the horizontal or vertical. Here what's really fun is that we don't know, for bits, if there is a diff between quantum and classical. So that's an open problem. Everything leads us to believe that it's not the case, but we haven't been able to prove it. So to tell you a bit about this problem, when I did my master project in Geneva, that's the question I got at the end of my at the end of the presentation. So I worked on a different graph, not the triangle, something else called bilocality. And then at the very end, like your jury asked question, and my advisor was like, "Oh, what would you do about that network?" And I said I had absolutely no idea. And then I worked on it like during my PhD with the same professor for 5 years, and I made really little progress. And it's really a frustrating case. But we saw a few cool things. This is what I'm going to tell you this morning, and they're like papers that are pretty fun to read that I will give as references later. So 3 variables, what can we do? Okay, if they have absolutely no connection, it's going to be model 1. So what I will do for readability, I will keep this thing big, and then I will just draw like kind of arrows and connection on the smaller things, and we're going to think, how can we test that? So the first model I'm going to speak about is basically, it's always ABC like there, so even if I put it very small. No connections, but we already seen how to test for that, right? If we have absolutely no connections, the joint distribution PABC is going to be just PA times PB times PC. And basically just to fix the notation, I can also see the distribution PABC as a vector in how many coefficients in the vector? So we'll have 8 components because I can, and I fix the notation once for all. I will put the P00, and then it's a matter of taste, but I increment the last one, then the second to last, until I get to P111. So that will be those 8 coefficients. Okay. Yeah. Oh yes, I started by saying I don't need to put it large enough, and then now it becomes crucial. Let's do that. PABC here as a vector, P000. Is that big enough? Good. P001 until I get to P111 at the very end. And this is in R8. Maybe before I start with this model, because I'm there and it's big, then I'm going to shift the model to the other board, and I'll do like the general stuff on this board and use the rest for the models. I already have some restriction about probability distributions. In particular, these two main restrictions are that if I sum over all possible events, so ABC equal 0, 1 cube, then of course the probability of something happening is 1. And then the other condition I can put is that the probability of some particular ABC can't be negative. I can't have negative probabilities. Before I move on to more complicated stuff, let me tell you something about how bad physicists are with notation. We are really sloppy. So normally, when you describe like random variables, the standard notation is to put here as subscript of the P, what are those variables you're speaking about. And here, you put kind of dummy indices that are just like algebraic variables, like they are placeholder for 0 and 1. So for example, if you want to say, let me give you an example, those placeholders, they will be important. If I want to say this probability distribution is symmetric under exchange of parties, what I would write is to say the probability of ABC taking, let's say, the value ijk is the probability of ABC taking the value, let's say, jki. So you see that there is a difference between what I put inside, which is basically for which value am I looking at the probability at, and here it tells you like which are the variables I'm looking at. What I want to say is that physicists are very sloppy because, and actually we love subscript and superscript to use them for other purposes. So sometimes people do just this. They just remove like what variable am I speaking of, and they just put the indices, and you can have to restore, recover, like deduce, or actually it's the P of ABC. So when you read papers, sometimes it will be a little bit confusing because this is not there. So in the list of reference I will give you later, I will make sure that at least the first paper you read, they are a bit more consistent.
Is this last condition very general or particular to this?
Oh, no. This condition that a distribution is always normalized when a sum over all possible events and that probabilities are non-negative, it's very general. Some people study, because you asked the question, some people study something called quasi-probabilities. So you can try to generalize this. If I have non-negative, I can have negative probabilities, but for events that I'm actually not observing, so I don't run into logical paradoxes. This is a thing, but I think it will be really confusing for like a first lecture in causal models to speak about them.
Symmetric condition is not really.
No, absolutely not. That was just, oh yes, thank you. Yeah. So that was just an example for the notation. And later on, I will show you, because when you impose symmetry, then you make the number of degree of freedom much smaller. So that enables me to show you some plots at the end. So I'm keeping that for later. So now for models. Like the first model I can construct is the variables are independent. And here I'm going to write exactly what I had over there. Is that PABC, it's PA of A, PB of B, PC of C, and for example, PA of A is the sum over BC of PABC, ABC. So that's, first one is very easy to check. It's not necessarily interesting to study that kind of stuff. Just want to be sure that I get my notation. So now what I'm going to do is to add like variables that I don't observe and make more and more general models until I get to things that are interesting. So another model would be A and B share a variable and C is not connected to anything. So what would be the condition to check for that? It's PABC. Because this is disconnected, I can write PAB times PC of C. And now I kind of split the problem in two. Because I know that when I do that split, this is very easy to characterize. If I just have a single variable, it's just normalization and non-negativity that I will have. And now I need to calculate that second part. But what we have seen in the example that was just on this board before is that if I have a common hidden variable between just two variables, this is basically, I can describe everything. So it means that we have completely solved that model. I can take any distribution. If it satisfies that equality, then I know it has a model of this form. Now moving to more and more complicated models until we get to something we can solve. I mean, easy. The next model is I'm going to add, again, a variable. C. What did I put this thing? Yeah, alpha. Again. So how do I describe this? I can't use the cheap trick I've used there of like using separation to factor the problem. But now I can realize that I can do this. In that model, so C only depends on alpha. And alpha also goes to B. We will check that later. But what I can do, I can twist this model around. So P of C alpha, I have that. But what I can also write so I'm going to put P alpha C is P C given A times P alpha. That's what I get. They can twist this model on its head. I can say that P alpha C is P of alpha given C times P C. Maybe I'll do an additional step there. So I have this, it comes from the causal model. C depends on A, and P alpha doesn't have any parents. So this is what describes the processing of an information there. What I'd like to do is to twist this part on its head and say that actually what happens is that I have C. C influences alpha, and alpha is given to Bob. And the fact that I can change the direction of this arrow is related to the cancer and smoking problem, that I can use bias rule to twist the probabilities around, and it still works. So what I will do now, if I wanted to do this part of the problem, what can I do? So now I need to write P alpha given C. But this I can actually write, if I know the distribution of C, this is equal to P alpha C. This is just bias everywhere there. So now I can relate those two things. So if I have a distribution of joint distribution of I alpha and C, I can actually find a PC and a P alpha given C. But this is just the marginal of this. I have PC equal to sum over alpha of P alpha C. So realize now I'm becoming very sloppy with the subscript, but you can still follow because the indices of the variable, they correspond to the letters I have on the graph. And this P alpha given C, to have this system consistent, I need to write that it's P alpha given C divided by PC. So as an exercise here, we could try to prove that PC and P alpha given C are probability distributions, that they are normalized and non-negative. And it will work, but I'm not going to do that here. The cool thing, if I reverse this arrow over there, it means I can also reverse the arrow on the other side. And now I know that these two systems are equivalent. And I can write everything that I observed there. Actually, this P ABC here, it's equal to PB given gamma, alpha and gamma, P of alpha given A, P of gamma given C, P of A, P of C, which is a bit long. But now I'm going to do a last step to transform this diagram. And I'm going to say that actually gamma is equal to A and alpha is equal to C. Okay, wait a minute. Alpha and C. So in essence, it goes like this. If I have a model of this way, what I can do is to replace this source here by something that contains the information that C will output. It's like giving an instruction to C, hey, this time you should say 0, this time you should say 1. And this variable will tell A, this time you should say 0, this time you should say 1. So now I can take this as the fundamental objects, and B, knowing what A and C have done, B can reconstruct gamma and alpha. So now what I can do is I can actually draw a bigger box around this recovery of gamma and this recovery of alpha. So I don't even need to assume that. I can just write it this way. Which means that I can replace that whole thing here by just PB given AC. And again, now, if I want to say, is my P ABC compatible with, okay, sorry. I should not use uppercase letters. I should use lowercase. That's a mistake. I'm going to correct it. This is A and this is A and C. This now is going to be P of B given AC, P of A, P of C. And this is again something I can check by, if I have a PABC, I plug A, I plug B. This P given AC I can compute using bias rules, but now it's two variables, and I can do that check. I see right now that maybe 50% of the audience is, if I get out of this room and you ask me to prove this again, I can do it again. I will take a picture of this. It's a really good exercise to practice like probability theory. I will make sure that this one I can like write it down and we can could like explore it later. I want to say that everything that we are going to do now is not as twisty variable as this one. It's going to be slightly easier. But I still wanted to do that example because it shows that in that model, I have an easy test of things. I'm not going to prove it, but actually everything you can do with quantum, if now you replace alpha and gamma by quantum states, everything you can do here, you can do with classical theories. So this will not be interesting for showing a difference between classical and quantum. I'm going now to erase that part. And this difference that quantum can be cloned, we will come back to it later. So now I will show you a model that always explains everything. The following model. A, B, and C. I know the variable, I put it in the middle, and it goes to everybody. Do you think there is anything I can observe that I can't reproduce with a model of that type? You mean? Is there anything, any distribution P, A, B, C that I could write down that will not be compatible with a model like that? So distribution here would be something like what I observe I sum over lambda because I can't observe lambda. And then A only depends on lambda. B only depends on lambda. C depends on lambda. And then I have the probability of lambda. And I sum over lambda because I'm not observing that variable. If I have a system like this, and A, B, C are bits, what I can actually do is to say that lambda is actually the value A, B, C. And I put that in the source. And then whatever I want to reproduce, I just distribute the lambda to everybody. and they will output it. So everything that I can observe, I can explain with a model with a common cause. To give you an example, I will call this the equal distribution. And it's a distribution that takes the value 1/2 if A equal B equal C and 0 otherwise. So they basically, A, B, C always output the same bit. This is very easy to explain. I put lambda. Lambda is also a bit, 0, 1. Everybody knows that lambda, everybody just outputs that value. And anything you can dream of, you can explain by this. You just have to say that lambda contains these 3 values and they're distributed and stuff. So this is not going to be a very interesting model. Now I show you like the thing that I worked for 5 years. I will erase that condition over there. And this, I will come back to it later. So the model that was really painful is, so now I have a question. I'm moving to the other side of the room, and you guys are going to have like an angle that's, I need to be careful to write big enough, right? The model is going to be this. A, B, C, and the variables only go to 2 of them. And A is 0, 1, B outputs 0, 1, C outputs 0, 1. And I have those 3 variables. I did something so that it's very easy for me to remember. I put alpha in front of A, I put gamma in front of C, and beta in front of B. And now the question is, what are the distribution ABC that I can reproduce with a model of this form? And it's actually a super hard question. What I did not specify in that context, alpha, beta, gamma, we can't observe them. So they can be whatever we want. They can be a bit, they can be a series of bits, of like, let's say 10 bits. They can be like 1 megabyte of information as a bit string. They could be vector in R3, they could be vector on the sphere. Whatever like classical variable you can think of, they can be that. So one of the first questions that we had was, if I observe a P, like first of all, what are the P ABC that are compatible with such a model and the ones that are not? And our dream was, of course, to replace alpha, beta, gamma by quantum states and find correlation that would come from quantum measurements that would not be compatible with an explanation with classical things. And that would be an example of advantage of quantum mechanics over classical physics. We're still looking for that example, so that's, maybe I'll leave the question. So one of the questions is the separation between quantum and classical. Another question is the characterization of the correlation. Characterizing the set of classical things you can do there. And the last question I'm going to speak about a little bit right now is the cardinality. I'll just check the time and see. Oh, we still have 25 minutes, which is good. I need a bit more space. Cardinality. Okay, those models in the middle, they were like things that were not that interesting, so I'm going to remove them. And small question, like we've been working for more than an hour now. Would you like a 2-minute break just, to kind of, or should I go on? Normally people say, like 45 minutes, you should always have a break, like they did studies on students. Just doing a bit of tea and we can go.
And I had a couple of questions about the model that you just shoved off.
Oh, perhaps. What was your question? Let's do that. Let's do that. What's the question?
So the simplification that you make at the end, no, in the model over there, in the second one.
This one or the one over here?
The one on the right, right?
Okay, yeah.
Yeah. So what you were in the end doing was the latent variables, gamma and the other one.
Yeah.
Right, was probably. They sort of became sort of not so fidel copies of A and B.
Yes.
So it's like you're transmitting information and you have something. So that is that sort of instantiates a causality.
No, it's more that the model I'm studying is this one. I'm not touching that.
Right.
But what I'm doing is I'm relating that model to a different model. I'm basically equating this one to this one. Oh no, crap! If I do that, nobody can see it.
Flip the arrows just to understand.
So basically, I flip the arrows. Like the end result is this. Then we can look at like, how do I flip the arrows? But basically, what I said is if it's compatible with this, it's compatible with that. These two models are equivalent. It doesn't mean that this is the explanation. But what I like about that diagram is that it's easy to write a mathematical condition for it. So even if I'm studying this one, I'm going there. And the way I do it is because C and A are terminal nodes. Like you don't need more information in alpha than just the value of this node. Because everything else can be reconstructed using bias rule. That would be the statement. The thing is, if I take, like, I don't know if you're satisfied with the answer. Probably it's like too short for anyone in the room. But because this is not exactly the kind of, we call that like this operation of moving things, we call that surgery. Like you would like to do surgery to repair a broken bone. It's to make things, to bring those diagrams to something we can compute easily. It's not something I will use in the remainder of any of the lectures. So like, I'll just give it like the short thing. We can discuss it over lunch, and I can give you references if that's okay for everybody. Because what's coming now is a bit different.
But I was just going to talk about this more, but if you want to keep going.
Okay, no, but if you have a question, then yeah, I'm happy to take it.
I just wanted to try summarizing what you were just trying to say.
Okay.
You turned that model into a linear chain, and then you said that the essential part of the linear chain is that C causes A.
Yeah.
And that cannot be distinguished from A causes C.
Absolutely.
From before.
Yeah.
So you can't write down the condition for this model because those two models are indistinguishable. You can at most reduce from measurements either say that C causes A or A causes C. Is that correct or
you said because the two models are equivalent, then I can't do something. It's more I can do something. It's like enabling.
What can you do?
So here I had some complicated math expression on the right that I could, like with the alpha and the gamma and the beta. By the way, I'm sorry to have erased. It was like too soon, but I prefer that I go back a little bit to it. Here I could not compute anything with it because I still had the alpha and the gamma, and I don't know what they are. I can't even represent them on a computer. But if I can use this trick and show that what I observed there is equivalent to what I observed here, in that diagram where I have these two arrows, I can write that P ABC is equal to PB given AC, that are now the parents, and now PA and PC are alone. So what I can't spend too much time right now because it doesn't fit is how I prove the equivalence of the two. But what I want to be crystal clear for all of you is that now for that diagram, because B comes from C and A, I can write that condition.
Right, okay.
And now that condition is easy to check.
Right.
That doesn't mean that my causal explanation is going absolutely to be this one. Because of course, if I observe something and it's compatible with this one, it's also compatible with this one, so you have no means to distinguish the two. But at least I can check. And if I see, for example, my thing is incompatible with both, then actually I'm not worried that they are equivalent. I just cross them and it's okay. If it's compatible, then maybe I'm not happy because I can't conclude anything. what observed is compatible with everything, then I can't do science. What I want is that it starts to be incompatible. So yeah, I want this to be clear that what we will do is always rewrite those graphs in a way that enables computations. I'm just checking with the timing because I had a nice example in the middle. I think I'm giving it, but I'm going to skip some parts, give you the reference to the paper, and I'll finish by like the inflation technique, which is the main thing that will be used. Okay, I can keep that for a little while, and I move to the next thing. So I will describe some correlation that are actually the example that my advisor gave me at my master defense, and I was unable to give the answer. So this distribution is going to be such that for ABC equal to 0, 0, or 1, 1, 1, the probability is 0. And all the remaining cases, it's probability 1 over 6. So from 0, 0, 1 to 1, 1, 0, probability 1 over 6 equiprobable. And now I'm going to give you a model for that. How do you use variables and how we can explain that. And it's a model that will use continuous variables like numbers between 0 and 1, which is actually very large when you think of it as information. Like real numbers, they have infinitely many bits in them. We'll try to find a model that's simpler. And there will be a nice puzzle. So the model is really nice. Wait a minute. Oh, what order did I use? B was there. So alpha and beta will share gamma between 0 and 1. I don't think everybody can read down there, but that's basically gamma. This gamma here is a real number between 0 and 1. Between A and C, I have beta, also a variable between 0 and 1. And the distribution is uniformly random. Like pick a number between 0 and 1. All of them are equiprobable. And alpha is also between 0 and 1. No, I need a bit more space. I will erase this. And so I specified, I say that, so not going too much in the details, but when you have continuous variable, you need to use probability densities that tell you, like for alpha between 0 and 1, you put the density over there, and the density is basically 1 if it's uniform. It's not that the probability of any point on the line is 1, it's that when you want to know the probability of it being in some interval, you just integrate over the density and you get the answer. And the same for all variables. So we specified what are the variables, and now what is A going to do? The response is that A is equal to 1 if the variable on the left is bigger than the variable on the right, and it's equal to 0 if the variable on the left is less or equal than. And then for B, 1 if the variable on the left is less than the right, and right, left, greater than, less than right. So why did I put left and right instead of variables? It's just to show you the symmetry of the model. And then I don't need to write Charlie. So for Alice, what she has on the left is beta, the value of beta, and what she has on the right is gamma. What Bob has, Bob is over there on the left. It's gamma, on the right it's alpha, and then Charlie, left, bigger than right, and 0 otherwise. And Charlie is on top, left is alpha, and right is beta. So that's a model that's perfectly symmetrical. Every source has the same distribution, uniform between 0 and 1. Every party answers according to the connection they have, left, right, is left, bigger, what I receive from the left bigger than what I have from the right. What I'm not going to prove is that this reproduces those correlations there that are what I call the not equal correlations, because it's correlation that forbid them to output the same thing, and all the 6 other answers are equiprobable. So how would you prove that this model reproduces this? You do as follows. The first thing is to realize that these 2 cases can never happen. Why? Because first of all, if they all output 1, it means that beta greater than gamma, gamma greater than alpha, alpha greater than beta. And if you write something like this, then you get that, which is a contradiction. So this case is impossible. But of course, now we have the other case, like 0, 0, 0. So that means 0, 0, 0, that means beta less than gamma, to have that, gamma less than alpha, alpha less than beta, from which you conclude that beta, beta is less equal to beta, so beta, oh, wait a minute. Yeah, if they are all smaller or equal than, then it means that they are all equal, because they will be all in the interval between beta and beta. So maybe there is a chance that this happens. But the thing is, it's continuous number between 0 and 1. So the probability that 2 numbers on the real line, like between 0 and 1, are exactly the same, that probability is 0. Something that's in probability, this one is called almost never. And it's a concept when the event actually could happen because there is no logical impossibility. But if you actually do the integration and you compute the probability, you get 0 because that's so small it can't be observed. So now we ruled out this case and this case. Then for the remainder numbers in the middle here, the first thing is because the model is symmetrical, you will have that 0, 0, 1 is equal to 0, 1, 0 is equal to 1, 0, 0. Because if you have the probability of that, you just rotate the diagram and you will have computed the probability of the others. And then the last step in the proof would be to say that if you change the condition, you say right greater than left, then it's equivalent to flipping, replacing 0 by 1. So the model has to be also symmetric under these flips. So it means that basically all these numbers are equal, they are all equal to 1 over 6. There is also explicit computation you can do. It's very lengthy, so just trust me on this. But now the question of my advisor was this. Let's know, that's kind of incredible. Here we have some correlation and they require infinitely many information in those 3 variables. Can we replace those variables with variable that takes finite values, like maybe integers between 1 and 10? And he thought, I think it's impossible. And I will give you his intuition, and then I will show you actually this intuition is not correct. But it took me 5 years to get to that point. Can you imagine that? Something that doesn't use much. It's not very complicated physics over there. That's very hard to tackle. So the idea is this. Note the things that I write in blue are going to be, maybe I start with at 1. Let's assume that this goes from 1 to n, and beta goes from 1 to n, and gamma as well. What we are going to impose is the symmetry. So now alpha, it's a probability distribution because it's number between 1 and n. So I don't need to use probability density anymore. I'll go back to probabilities. So the probability of alpha taking a value is the same probability for beta and the same probability for gamma. For example, it means that if alpha is between 1 and n, equiprobable, then all the other variables have the same distribution. And also going to assume that A, B, and C, they have also symmetric response function. Not necessarily comparing the number and outputting the result of the comparison, maybe something else, but it has to be symmetric. Because why not, We have symmetric correlation, physics is all about symmetry, so let's keep a symmetric model. And then you see that it can't work. Why? Because let's look at this, at the cases. Now, what will happen is that the probability of alpha, beta, gamma having the same value is not 0. It was 0 before because there were like number on the continuous line, and the probability of like, you know, infinitely small things to like overlap is 0. But now they have like the probability of alpha being 1. It's something that can happen. So it could happen that all alpha, beta, gamma are equal, let's say, to 1. Okay. But now the thing is, A, B, and C will receive, each of them will receive the same information coming from the left and right. And we said that we want to preserve symmetry, so they will all use the same decision function to output something. So now there will be a non-zero probability that they output something that will be the same. I will not go like much more on this. It's a bit unwieldy what I did. I will give you the reference to the paper. Was this like enough explanation for that thing? Like, who is convinced by this proof? Like okay, not so many people. What time is it? Let me check. What I will do is give you the reference, and then I move on to the next topic. So to see that argument, the paper would be, hey, where is my notes are over there. And I'll move then to the last example. So the cardinality thing. So it's a paper, it's on the archive. You should look at archive number 1709 0707. What I wanted to give you as a taste here is that for this particular correlation, if you want to preserve symmetry, you have to keep infinitely many values for each of those variables. So if you have physical system, then it's something like infinitely many states. You can't reduce that. And then that became the question of my PhD, like, can you, because a symmetric model doesn't exist, but maybe if you break the symmetry, you will find an explanation. And then the case was, if you want to explain all possible correlation you can do, can you always do that with, let's say, cardinality 10, like 10 values for each of the variables? And in this paper, what did I have to do? One sec. In this paper, we proved that you need only 6 values. So read the paper. It's a pretty simple paper to read and get into those things. Sadly, I don't have time much to devote to this proof because I need to move to the next example. I will erase this on the left. And Gibran, question of timing. Are we sharp to finish at 12:20, or can I go until 25 because we started
as
a
long
bit?
as the audience is okay cutting into their lunchtime. That's
okay.
Working with 4 parties or n parties as well, so introduce another value, for example. How would it
Oh, you mean having more parties in this model?
Yeah.
Oh, it's already hard with 3, so we are not even trying with 4. But we could discuss it over lunch, like what to do with 4. So I'll try not to cut too much in the lunchtime. I think we started a few minutes late, and maybe a few minutes late, if that's okay with everybody. Other option is that I shift part of this into the next session, up to you. If there are no complaints, then I'll continue. Maybe a few minutes over.
Yeah, that's fine.
So now what I'm going to do is to show that this distribution, which is equal to 1/2 if A is equal to B is equal to C, and 0 otherwise. And this I will call the equal distribution. I will show that it's impossible to do with a model. Okay, I don't have the model. Quickly going to do it again there. It's incompatible with a model of that shape, where you don't have any common information, only a variable shared between each time two of the parties. And the way to do that is to use the inflation technique. And it's a very clever and very simple technique. I will give you the archive reference. It's 609-00-672. I mean, some of the references have been published, but I prefer to give you archive numbers because it's much more compact to write. This is a 46-page paper. It's pretty not nice to read if you really read it back to front. But if you just keep the things that are pretty abstract and you just focus on the examples, it's really like the examples are really nice. So many colleagues have been like put that under the pile because they don't want to read it, and they did not realize the power of that technique. I encourage you to read, but just skip and you do examples. I will do one of the examples, and it's a pretty striking one. So the problem here is that it's very difficult to compute with this. Because what we would have to do is to check, so I have my PABC here, is it compatible with something where I have a distribution for alpha, a distribution for beta, a distribution for gamma, because alpha, beta, gamma, they don't have any poses that go to them. Then A only depends on beta, gamma. B only depends on gamma, alpha. C only depends on alpha, beta. Another question I ask, does there exist a P alpha up until a P C given alpha beta such that this equality is satisfied? And of course, all this should be probability distribution, like sum to 1 and non-negative. The problem is that before I worked on this cardinality business, there was no possibility to know even like how many values should I take for alpha, beta, gamma. Like when I ask for the existence of a distribution here, I mean a vector P alpha such that I can go P of 1 until P of n alpha if I have n different values for alpha. If I don't even have a bound on how many alpha should I consider, then I can't even solve the problem. Luckily, we now have bound at 6. It's proved in that paper. So now, oh yeah, nice. We have a system with a polynomial of degree 6 over 6 plus 6 plus 6, 18. Here it's going to be 6 times 6 times 2, 72, 72, 72 variables. Try to put that in Mathematica and your computer will like burn in flames. So we need to find something else. Now I will show you like one way to do that example. What I want to say is that here we have a number 6. We don't even know if that bound is optimal. So maybe you can take this paper and try to crush the bound a bit. I'm a bit where space. I will erase this board if that's okay with you. I'll keep the reference there. And timing, yes, 5 minutes more and we are done. So let's do something. I finished this. You may have questions. I can answer them during lunch, or I'll do at the start of the next session. Aircraft. That was 1609. At the start of the next session, I will take like your Q&A on this. So don't just come to me during lunch. 17. 17, yes. Thanks a lot. There we go. So how do I show that this is impossible? I will use something that's called inflation. So here I have my original diagram. And what I will do, I will move my variables around. So what I'm going to do, I'm going to put my A, my B, and my C like that. And I put small indices to distinguish them. And I'm putting also my sources there. So what I'm going to do, I assume that if I have a wiring of that diagram between causes and effects that works, I can take the same devices, maybe actually copies of them, and wire them differently. So what I've done here is exactly the same as there. It's all the beta is going to be wired that's going to be different. So I put a beta 1 here and a beta 2 over there. What it means is this. Here, I think I have a device that produces this value beta, and that value beta is transmitted to A and C. What I'm doing in that diagram here, I'm not doing a copy of beta. What I'm doing, I'm building another device that has the same distribution of beta that it produces, and I'm wiring one of them to Alice and one of them to C. But of course, if I look at beta 1 and beta 2, they are not correlated. They have the same distribution, but they are independent.
They're not relating beta 2 to A, right?
Beta 2, yes, that's a good point. Beta 2 has a second output because normally it goes to both boxes. What do I do with this? I just put it into the trash can. And what I do with the other wire that comes out of beta 1, trash can as well. So it's something I assume in my theory that I can always like produce a physical system and just throw it away, which is something that we can do with information, say we just don't use it. So the thing is that, so that's the original scenario, that's what we call an inflation. Nothing to do with like inflation of the universe, just that we create copies of things and wire them differently. And of course, the correlation produced by A, B, C here, they are not the same as the one that we produced there because we did something different. But what's going to happen is that if I just look at this part, what I have inside here is exactly the same as what I have inside there. So what I'm going to say is that if I do observation just on A1, B1, and I ignore what's outside, so there is no influence of C back on there. There's no influence back. So if I remove C1, whatever wiring I do outside of my lab, I'm not going to see the effects because I don't have information about what's going on in my lab. So what I can say is that the probability in the graph of the left of the variable AB taking some value ij, it's exactly the same as what A1 and B1 take for values ij over here. I said 5 minutes. Let me check that I'm on track. Oh, it's now. I'll finish and we'll come back to it at the next session. So I could relate A1 and B1 said they're equal by this argument. Just not to leave you hanging, I can play the same game with BC. I will have exactly the same thing, but I will need to consider a different subgraph. And BC, they will relate to B1, C1. They are the same. But if I have correlations that are A, B, C are always the same, then what it means in that graph is that I just have proven that A1 is equal to B1 is equal to C1. Because I made that link by comparing that, and they are equal there. I made that link by comparing them, they are there. But now if I just look at A1 and C1 and I remove B, they are not independent in that graph. Whereas they are not independent in that graph. So I will obtain here that the probability of A1, C1 from that conclusion, it's equal to 1/2 A1 equals C1 and 0 otherwise. If I remove B1 and observe what's coming there, I will see that A1, C1 factorizes. I'll come back to this later because that's the punchline and we will not have time to process it. what we have there is that we have a contradiction. So it means that this can't work, but we have that if the original worked, then the inflation worked. But now we prove that the inflation is not working. So that implies that the original was not working either. So that's the proof by contradiction. What I will do, I'll come back to that at the next session. And I think we can all go to lunch, right?